Hello, this is Shifali, and in this video you will learn how to calculate space complexity of an algorithm. It is the next sequel of my previous video on space complexity. So, as you know, space complexity of an algorithm is the total space taken by algorithm to complete its execution with respect to the input size. It consists constant space and auxiliary space. Constant space is one which is fixed for an algorithm. Generally, it equals to space used by input and local variables, while auxiliary space is extra or temporary space used by an algorithm. Now, there is one point to note that constant space is generally ignored. People often calculate only extra memory needed, not counting the memory needed to store the input itself. Well, that's what smart people do because memory used by input and local variables is always expected to be consumed by an algorithm. So it's quite smarter way to include only auxiliary part or to calculate only auxiliary part and ignoring the constant part. Now let us see few examples. Here we have three functions 1, 2 and 3, and we'll calculate space complexity of each of them. These functions are written in Python, and if you don't understand Python, don't worry, just think of them as simple algorithms. I'm sure you will get them. Let me explain you what this first function is doing. The name of the function is calculate. It accepts three input variables which are integer in our case and returns some mathematical calculation of those input variables. Now, in order to calculate space complexity, we assume that space required for one variable is equal to 1 unit. We assume it just for the sake of simplicity. Now let's calculate space complexity of this first function. We'll start with the inputs. So, one amount of space, 1 unit space will be consumed by variable A, 1 by variable B, and 1 by variable C. And then not any other space is required to execute this function. It's just returning some mathematical calculation of those inputs only. So the total space consumed by above function is given by this expression, which is equal to 3 and which is in turn big O of 1. Aha, we have done space complexity of a function. Now let us see one more example. Here we have another function sum, and it accepts two variables a and n, where a is the array of integers, or in terms of Python it is list of integers, and n is the length of the array a. And what this function do is return sum of elements in the array a. Now let's calculate its space complexity. So space consumed by variable a is equals to n into 1, because a contain total n number of elements, and each element in a will consume 1 unit space. So total space consumed by variable a is equal to n into 1. Then 1 unit space will be consumed by variable n. And now if we move inside the body of the function, there is one local variable s, so 1 unit space will be consumed by it. Then there is a temporary variable I for this for loop, so 1 unit of space will be consumed by this, and not any other space is required to execute this function completely, because while executing this statement, the value of s is updated on the same place as in memory. Not any other space is required to execute the function. So total space required for above function is given by this expression, which is equal to big O of n in asymptotic notations. So we have done space complexity of this second function too. And now if we try to be a bit smart and consider only auxiliary space, it is equal to big O of 1. ignoring the constant part and considering only extra or temporary space used by the function, is equal to auxiliary space, which in this case is equal to only 1. So it is big O of 1. Now let us see one more example. So here we have our third function, and what this function is doing is the same what above function does. Return sum of the elements in array A, and n gives the size of the array A. But as you can see, it is a recursive function, and calculating space complexity of a recursive function is not so easy, because whenever a function calls itself in recursion, whenever a function calls itself, what happens is the state of calling function is stored on stack, and then the called function is executed. So while calculating space complexity, we are supposed to calculate the space used in that stack also, and that comes under auxiliary space, because that amount of space is consumed by this function to execute for temporary amount of time. So it's not so easy to calculate space complexity of a recursive function, but there is a short trick. To calculate only auxiliary part of a recursive function, we have a formula, which is number of stack frames required multiplied by space per stack frame required, and this whole expression together will give us total auxiliary space required to execute any recursive function completely. Now let's try to calculate space complexity of this function written over here. So first we'll calculate space per stack frame required. So when this function calls itself, when this rsum function calls itself, there are three things that are stored on stack. The array pointer A, that is this one, then the size of the array, that is this n, and then the last value at the index A, that is this one. And then the function, the called recursive function, will execute. First these 1, 2 and 3 things will store on stack, and then this function will execute. So space per stack frame is equal to this expression. Now we require to calculate number of stack frames required. So in order to calculate the number of stack frames required, we calculate how many times this function will call itself. This function will call itself from n minus 1 to n minus 2, then n minus 3, then n minus 4, till n becomes 0. Because when n becomes 0, it will be no more calling itself again, it will just return 0. So this function will call itself till n becomes 0, from n minus 1 to 0, which is equal to total n times. So we got number of stack frames is equal to n, and we also know that space per stack frame required is this expression, which is also written here. So total amount of space required to execute this function is given by number of stack frames required, which is n, and number of stack frames, space used by each stack frame is, which is this one. So total space is this into this, number of stack frames into space per stack frame, this n into this expression. So this expression whole together give us auxiliary space required to execute the above recursive function completely. But as we can see, the value inside the bracket is constant for a particular input. So we can say that space complexity of this function, of above function, is directly proportional to n, because n into some constant. So it is equal to big O of n. Space complexity, auxiliary space complexity of above recursive function is equal to big O of n. So congratulations, we have done space complexity. Thanks for watching the video. If you liked it, don't forget to hit the like button below. Keep learning and sharing. Thank you.